Boy, boys, I think we got our hillbilly version of getting them into computer engineering down. We got the first step. For sure, that's this bad puppy. Where are we living? We want to live here. Be up in here. How to program the marshmallow. Stuff this thing in your mailbox.
Alright, so what you're looking at here is a program called Logicin. It stands for Logic Simulator, most likely, or something like that, because it's a program where you make logic circuits. Now, if I had to describe what a logic circuit is it's basically an electronic circuit made up of things like transistors that performs logic on binary signals. And a binary signal is a signal that has one of two states, either on or off. Now I've got some examples down here of some logic circuits, specifically some logic gates, which are circuits that do specific operations. They do specific things. And I've got the logic gates right here. Over here on the left, I have toggle switches, where each of these little boxes is a button. Each one of these circles is an LED representing what the state of that toggle is. And these LEDs over here show what the output of each of the logic gates are. These green lines right here are wires, with dark green being off and light green being on. So this is an AND gate, and it's called that because, let's say, these two things are inputs A and B, and this is the output. The output is on only if A and B are on. So if I go and I turn A on, nothing happens. If I turn just B on, then nothing happens. But if I turn A and B on, then the output is on. Now another way to refer to this instead of saying on or off is true or false, where false is off and true is on. This is an OR gate, and it's called that because it'll be on or true if either A or B are true. So I can turn this one on, this A input, and it's on. I can turn this B input on, and the output's on. And I can also turn both of them on, and it'll still be on. This is a NOT gate. It only takes one input, and it basically inverts it. As you can see, the input is off or false, and the output is true. So if I turn the input on, then the output turns off. And okay, it's not turning off. I don't know why it turns the simulation off when I do that. Sometimes. That's weird. Anyway, you can make all sorts of different circuits that do all sorts of interesting things with combinations of these various logic gates. And this certainly doesn't look like logic gates because it's not. It's the very top level. Inside each one of these little boxes is a whole array of logic circuits. As you can see, this one's little tooltip indicates that it's a ZE 8-bit microprocessor. ZE standing for Xenon because I made it. And this right here is a 32 by 32 LED matrix, and it's all off right now. And this right here is a ZE 32 by 32 display controller. It basically controls this display. You can see that it's only got a few inputs, yet it controls this whole thing, and I'll get to how stuff like that works later. This right here is called a ROM. If you don't remember what a ROM is, it stands for read-only memory, or read-only memory. And it's memory that can only be read. So, examples of something like ROMs would be DVDs, even though you can burn some DVDs, so those are actually called DVD. I don't actually remember what they're called, but there are DVD ROMs, and like if you remember the older game consoles, those had ROM cartridges that you plug in, and that's memory that can only be read and not written. And this over here, this component, is RAM, which stands for Random Access Memory. It can be written to and read from anywhere in the memory. Like any place in it, inside this RAM, can be read at any time, or written to. And this one, in particular, has 64K of RAM, which that doesn't sound like a lot, And it really isn't by today's standards, not at all, but this is an 8-bit microprocessor that's running it. So it should be fine, especially considering that this is a 1-bit LED matrix, I should say, because the lights can either be on or off, which means that it only takes up 128 bytes, in memory. And that's a tiny portion of that whole 64K. And that means that stuff like sprites and graphics like that are also going to be really tiny. So it just works out in the end. And this chip right here is called a Northbridge. And a Northbridge is a chip that basically routes things coming from the CPU to the rest of the computer, and things from the rest of the computer to the CPU. And nowadays, that kind of chip is usually built into the CPU itself, but in older systems, it was a separate chip, like it is in this one. Now, I guess I'll go ahead and show you the CPU. If I click View This, now it looks like a mess of wires, doesn't it? Well, just wait, it gets worse. Let me zoom out. There we go. This is absolutely awful. At least awful to look at. It performs amazing things, like math and other things. But anyway, it is not very easy to tell what anything on this does at all, because it's just not intuitive. It's all logic circuits. But I'll just go ahead and point out that this, and this are the inputs and outputs. Now, the address is an output. And what the address is says where in memory we're currently looking. Whatever we're doing there could be reading or writing, but the address just says that's where we're looking. And since there's a ROM and there's a RAM, there's also a graphics memory, this address can point to one of those three depending on where it is. The very bottom addresses, the ones closer to 0, go to the ROM. And the ROM's only, I think it was 1 kilobyte, I think? Yeah, probably. And the RAM takes up the majority of the address space, and it does not have its full 64K actually accessible because it's using the same address space as a ROM chip and the graphics. And the graphics is the very top 128 bytes of the address space. And this right here, this data bus in, what a bus is basically like a highway for data. It's what the data travels across. And this particular one is coming in. And you can see we've got 00101111. And I think that corresponds to, I don't know what it corresponds to. I don't. But what it actually is, what I know it actually represents, is an instruction. Because it's at address 0, which means it's looking at the very first byte in the ROM. And I know what I put in the ROM. The first thing that's in there is an instruction. And the first thing that instruction does is copies a block of other instructions into the RAM. And then it jumps to the RAM and starts executing from there. So, yeah, and this data bus out is whatever data is coming out of the CPU. Now, that's just a tiny part. And there's a lot of things on this, and I'm not going to go through every single one. So, I'm just going to split it up into chunks. This chunk right over here in the top left, this is it's like the control center. This is where everything comes in and out of, and where everything gets routed to into the CPU, or the thing that routes everything in the CPU, and that controls what things in the CPU are functioning and when. For example, this right here that I just pointed at is the instruction register. That's where the instruction lives while it's being executed. And this is the program counter. No, that's not the program. This is the program counter. It basically says where in memory we're executing. Of course, it can be overwritten by other instructions, if you want to jump somewhere. This counter represents what part of the instruction cycle we are in. And it's made up of 4 cycles. And these 4 lines represent which part of the cycle we're in. The first one is fetch. That is when we're getting an instruction or data from memory. The next one's decode. And that is, if we just got an instruction, it's figuring out what am I supposed to do with that instruction, and preparing to do that thing with the instruction. Then we've got execute. Technically, these two are both kind of execute, but I'll get to that in a second. The execute is the signal that says, okay, it's time to actually do what we're supposed to do. And then this last one, it's kind of finalization. There are some things that have to happen after execution before the next instruction can be executed, like for example, incrementing the program counter, resetting certain things that need to be reset, etc., etc. Anyway, not all instructions take one whole cycle to execute, like this whole cycle of fetch, decode, execute, also execute. There are several instructions. In fact, most instructions take more than one cycle to complete. Some examples of some instructions that only take one cycle to complete, and I should probably show you
BB,
instruction
Mason
set
Robot, BB.
architecture, which is basically the instructions that the CPU knows. If I look at this, we've got these 29 instructions. And this NOP, which stands for no operation, it takes one cycle because there's nothing that it has to do. And some other ones that only take one cycle, let's see, add, subtract, multiply, divide, negate, compare, left shift, right shift. I think, this one, the Y copy to A, the Y copy to B, Y copy to the lower part of the address, Y copy to the higher part of the address. Not that one. The logical not, logical and, logical inclusive or, logical exclusive or, and the modulo operator or remainder. I believe those are all things that only take one cycle to execute because they're really simple. The operands, or things that they're working on, have already been provided by other instructions. For example, this load A and load B, these take 2 cycles, I believe, because the first cycle is, of course, decoding the instruction and preparing to execute it. And the next cycle is actually getting that data. So the thing is, if you have an instruction that needs outside data, it will take at least more than one cycle. Because for each given cycle, you can only work with the data that you already have inside the CPU. So if there's any data that needs to come from outside, it can't happen until after the first cycle. Now, an example of a really, really, really long instruction is the copy instruction. Except, it's a little bit different. I'll get to that one in a second, so I'll instead draw your attention to the jump conditional. Jump if the specified condition is met. So you've got 2 bytes for address and a byte for the condition of whether or not to jump. So yeah, that takes, I think, technically 4 cycles, because on the last cycle it's actually doing the jump. And yeah, so that's one of the longer instructions. And I'll go ahead and get back to the CPU. And what's some other things that probably need pointed out? Oh yeah, I was in the middle of like what chunk to do what. We just finished with the little control chunk. Then we've got this whole line right here in the middle. This really, really, really long line, plus also this kind of, and also this. That is the decode logic. That's what actually decodes the instructions and sets them up, or sets the CPU up for what those instructions are telling it to do. This over here is the arithmetic logic unit. You put information in, you send signals to do various computations, which are what these green wires are. Those are signals to do various computations. And if I zoom in, there we go. This register that I call the Y register, that's where